The universe is a place of unimaginable wonders. It stretches further than we can truly comprehend. Among the most fascinating of these are black holes. They are regions in spacetime where gravity is so incredibly strong. Nothing, not even light, can escape their grasp once it crosses a certain boundary. This boundary is known as the event horizon. Black holes challenge our understanding of physics itself. They are truly cosmic monsters, yet they hold keys to understanding the universe. Black holes are not empty space, as their name might suggest. Instead, they are an enormous amount of matter packed into an incredibly small area. Think of a star many times more massive than our sun. Now imagine all that mass squeezed into a space smaller than a city. The result is a gravitational field so powerful it distorts space and time around it. This warping of the very fabric of reality is what makes black holes so unique. They are a direct consequence of Einstein's theory of general relativity. For many years, black holes were purely theoretical concepts. Scientists debated their existence. Could such extreme objects truly form and persist in nature? The evidence slowly began to build. Astronomers observed stars orbiting invisible companions. They detected powerful X-rays coming from regions where nothing could be seen. These were tantalizing clues. They hinted at the presence of these gravitational behemoths lurking in the dark. Black holes are born from the death of giant stars. To understand their formation, we must first look at the life cycle of stars. Stars are born in vast clouds of gas and dust called nebulae. Gravity pulls this material together. As it clumps, the core becomes hotter and denser. Eventually, nuclear fusion ignites. Hydrogen atoms fuse to form helium, releasing enormous amounts of energy. This energy pushes outwards, balancing the inward pull of gravity. This delicate balance allows a star to shine steadily for millions or even billions of years. Our own sun is currently in this stable phase. However, not all stars end their lives quietly. The fate of a star depends on its mass. Smaller stars, like our sun, will eventually run out of hydrogen fuel in their core. They will expand into red giants, then shed their outer layers. This forms a beautiful planetary nebula. The core will remain as a white dwarf, a dense, cooling ember. But for stars much more massive than our sun, the story is far more dramatic. These giants burn through their fuel much faster. They fuse heavier and heavier elements in their cores, from helium to carbon, then oxygen, and eventually up to iron. Iron is a critical point in a massive star's life. Fusing iron does not release energy, it consumes energy. This means the outward pressure from fusion suddenly stops. There is nothing left to counteract the immense gravitational force of the star's own mass. At the heart of every black hole lies the singularity. This is a point of theoretically infinite density. Here, all the mass of the collapsed star is crushed into an infinitesimally small volume. Our current laws of physics, including general relativity, break down at the singularity. We cannot truly describe what happens there. It is a region where space and time as we know them cease to exist in a meaningful way. Understanding the singularity is one of the greatest challenges in physics. It likely requires a new theory that unifies gravity with quantum mechanics. Surrounding the singularity is the event horizon. This is not a physical surface you could touch. Instead, it is a boundary in space-time. It marks the point of no return. Once matter or light crosses the event horizon, it is trapped by the black hole's gravity forever. It cannot escape. The size of the event horizon, known as the Schwarzschild radius, depends on the black hole's mass. More massive black holes have larger event horizons. For a black hole with the mass of our sun, the event horizon would be only about 3 kilometers in radius. The idea of objects so dense that light could not escape them predates Einstein's theories by over a century. In 1783, the English natural philosopher John Michell first proposed the existence of dark stars. He reasoned, using Newton's theory of gravity and the corpuscular theory of light, that a sufficiently massive and compact star would have an escape velocity greater than the speed of light. Light particles, he thought, would be pulled back by gravity. A few years later, in 1796, the French mathematician Pierre-Simon Laplace independently proposed a similar concept. These early ideas were fascinating, but lacked a solid theoretical framework for how such objects might form or behave. The true theoretical foundation for black holes arrived with Albert Einstein's theory of general relativity, published in 1915. This revolutionary theory described gravity not as a force, but as a curvature of space-time caused by mass and energy. Massive objects warp the fabric of space-time around them, planets and light rays then follow these curves. Einstein's equations were incredibly complex. For decades, black holes were invisible enigmas. We could infer their presence, but we couldn't see them directly. After all, how do you photograph an object that absorbs all light? The challenge seemed insurmountable. However, scientists are ingenious. They realize that while the black hole itself is dark, the superheated material swirling around its event horizon should glow brightly. If a black hole is backlit by this glowing plasma, it should cast a shadow. This shadow would be a dark region corresponding to the event horizon. Capturing this shadow became a monumental goal. This ambitious task was undertaken by the Event Horizon Telescope, or EHT, collaboration. The EHT is not a single telescope. It is a global network of radio telescopes, spread across different continents. These telescopes are linked together using a technique called Very Long Baseline Interferometry, or VLBI. This technique allows them to achieve the angular resolution of a single telescope effectively the size of the Earth. This incredible resolving power is necessary to see something as small and distant as the shadow of a supermassive black hole in another galaxy. After years of preparation, observations and meticulous data analysis, the EHT collaboration announced a historic achievement on April 10, 2019. Because black holes themselves emit no light, astronomers must act like cosmic detectives. They search for clues and indirect evidence of their presence. One of the primary methods is observing the gravitational influence of a black hole on its surroundings. For example, stars orbiting an unseen massive object in a galaxy's center can indicate a supermassive black hole. By tracking the orbits of these stars, like those around Sagittarius A** at the heart of our Milky Way, astronomers can calculate the mass of the central object. If the mass is enormous and confined to a small space, a black hole is the most likely explanation. Another key method involves detecting radiation from material falling into a black hole. As gas and dust are pulled towards a black hole, they form an accretion disk. Friction within this disk heats the material to incredibly high temperatures, millions of degrees Celsius. This superheated plasma emits intense radiation across the electromagnetic spectrum, particularly in X-rays. Space-based X-ray telescopes like NASA's Chandra X-ray Observatory and ESA's XMM Newton are crucial for detecting these X-ray signatures. Black holes are not just isolated curiosities, they play a fundamental role in the cosmos. In particular, supermassive black holes, or SMBHs, appear to be key architects in the evolution of galaxies. Most, if not all large galaxies, including our own Milky Way, are believed to host an SMBH at their center. These behemoths can have masses ranging from millions to billions of times the mass of our Sun. The presence of such massive objects at the heart of galaxies suggests a deep connection between their growth and the development of the galaxies themselves. There is a fascinating observed correlation between the mass of a galaxy's central bulge of stars and the mass of its central SMBH. This relationship implies that galaxies and their central black holes somehow grow in tandem, influencing each other's evolution. This is known as black hole galaxy coevolution. How this coevolution works is a major area of research. It seems that the black hole doesn't just passively sit there, it actively interacts with its host galaxy. This interaction can have profound effects on the galaxy's ability to form new stars. Despite tremendous progress, black holes continue to guard many profound secrets. One of the most perplexing is the information paradox. According to quantum mechanics, information can never be truly lost. However, general relativity suggests that anything falling into a black hole, including the information it contains, is lost forever beyond the event horizon. This apparent contradiction between two fundamental theories of physics is a major puzzle. Scientists like Stephen Hawking propose that black holes might slowly evaporate via Hawking radiation, potentially releasing information in a scrambled form, but the debate continues. The study of black holes is a journey into the unknown, and the future promises even more exciting discoveries. Technological advancements are continually pushing the boundaries of what we can observe. The Event Horizon Telescope collaboration plans to expand its network by adding more telescopes. This will improve its resolution and sensitivity. Future upgrades could allow for even sharper images of black hole shadows. We might even be able to create movies of material swirling around event horizons. This would provide unprecedented insights into the dynamics of these extreme environments and test general relativity with even greater precision. Space-based observatories will also play a crucial role. Future X-ray telescopes with greater sensitivity and resolution will allow us to study accretion disks and jets in more detail. They will help us understand how black holes feed and how they influence their surroundings. Furthermore, space-based gravitational wave observatories like the Laser Interferometer Space Antenna, or LISA, are planned.